sorry. Where is it? Is it close or? Okay. Right. So essentially, we introduced D as some sort of other way of measuring the electrical field that does not depend on the material. But we said at the time that this is not the whole story of what D is physically. What is D actually measuring? Right. And this all goes back to the electromagnetic model. So we know there's a particular way of thinking in EM theory where we think about how material mediums are modeled, how charges are modeled, and everything is modeled. And there's some subtlety to the electromagnetic model that we have not introduced yet. So it's not the whole story of what D is. And we're gonna talk about that now. D is gonna be something called, turns out essentially what it is, it's a measure of something called polarization. And we're gonna talk about what polarization is today. Right? So epsilon naught is a property of free space. But the idea is that if you have something other than free space, you would have epsilon, some other value, not other than epsilon naught. This implies that so epsilon naught is a way of measuring a property of what's called the dielectric material or medium. Dielectric medium, any material it has a dielectric property, and this model incorporates the concept that free space itself is a kind of dielectric. Okay. Before we go over any further, we have to explain the concept of bound and free charges. Up to this point, when we were dealing with charges, we were dealing with free charges, meaning we have our space, and then we could have point charges, we could have line charges, we could have surface charges, we could have volume charges distributed over space. But those are charges distributed over space, and those are called free charges, meaning those charges can move. So this charge can move anywhere. This sheet can move anywhere, right? So those sort of charges that are in space, for example, this chalk might be charged in space. They could throw it out. You might throw it. It's free to move in space. That's what free charge is essentially. Free charge is charge that's free to move in space. Okay, but there is another concept of charge, which is called a bound charge. Bound charge, I mean, simplest way to explain it is that it's not free to move in space. It is tied into space. It is kind of like let's say you have a shirt with beads sewed over it, and those beads cannot move away from the shirt, right? So if the whole shirt can move, imagine that three-dimensional space is a shirt. Yeah. Yeah, that's a tortured analogy, but yeah, imagine that. And then the beads are tethered, are sewn into the fabric of space itself. So bound charges are charges that are tethered into the fabric of space itself, and they cannot move from one point to another. They exist, but they cannot move. Those are essentially non-free charges, bound charges. And they literally exist like in the electromagnetic model, in EM model. The assumption is that free space itself, empty space is not empty. The assumption in the model is that in every point in space, there is charge. But why is the space, empty space, not charged, neutral? Well, because there's an equal number of positive and negative charges. So at every point in space, there is positive charge and negative charge equally. And they're tied, they're sewn into every point in space. They cannot move. The charge at one point cannot move to the charge at another point. This is called the bound charge model of space. Is it true? Is it literally true? Well, classical EM is not the whole story of free space, right? It's a classical theory. So kind of like how Newton's theory is correct in many ways, but it's not absolutely correct. we kind of went beyond it. Same thing. I mean, this is not literally true, but this is literally true. This is true in the model of EM. And this is enough. It is accurate enough for us to predict radio waves and transmission and reception and electromagnetic slew of electromagnetic phenomena. Okay, right. So this is an EM model. The EM model presupposes that at every point in space you have stitched into the space structure equal number of positive and negative charges. This is sometimes literally true. Well, many times this is literally true. When is it literally true? If you have a slab of material, not empty space, a slab of material that's not a conductor. Let's say this is, I don't know, glass. Right? We know that this has atoms, right? And the atoms have a positively charged nucleus and a sea of electrons around it, right? We know this to be literally true. Well, those atoms in the crystal of the glass that cannot move, along with the clouds of electrons around them that cannot move, those protons and electrons that are fixed in space, those are bound charges. Those are literal bound charges. Okay, so it is possible to have literal bound charges depending on the material because of the atomic model, right? Atomic reality. But even what I'm trying to press is that even beyond that, EM theory, the EM model itself presupposes that even empty space itself has those kind of bound charges. When you have those kind of bound charges, any bound charges, you have something called polarization that could happen, right? Polarization, by the way, can happen even for free charges. Essentially, what polarization is you have dipoles, and then you have an external field, and the external field is going to align the dipoles so that they match the field. Essentially, like a compass. If you have a compass, although this is magnetism, not electric static electricity, but it's the same concept. You have a compass, and then you have the Earth's magnetic field. And then the compass is going to try to align with the Earth's magnetic field. Essentially, that's the same thing. That's polarization. The alignment of the compass is magnetic polarization. The bound charges, bound dipoles, when they align with an external field, that's electrical polarization. Okay. So the way to understand dielectrics is to understand how the bound charges, either the bound charges supposed to exist in free space or the bound charges that exist in materials, how do they align with an external field? How do they stretch and orient? That measure of how they align and stretch and orient is called polarization. And that is the key to modeling the effect of material on the into the electrical field. Right? We're concerned mainly with polarization of bound charges. Okay, what is polarization? Let's define polarization. Polarization is a source of electric field. It's one of the sources of electric field, right? What is it essentially? You know how you have point charges and then you have charge density. A point charge is a concentration of charge in one point. A charge density is a smearing of the charge over a region of space, right? In the same way, polarization ties to dipole moments. So we studied a vector source of the electrical field, which is the dipole moment. Essentially, dipole moment is one positive and negative charge very close to each other, right? But this is the dipole moment is akin to the point charge. It exists at one point in space. If we take this dipole moment and we smear it over a volume of space, so this is like the dipole moment smeared over dv prime, let's say, a small region of space, or any region of space, really, volume of space, this smearing, in a similar way that the smearing of the point charge gives me charge density, the smearing of the dipole moment gives me polarization. That's what polarization is. It's the continuous smeared version. It's the density version of the dipole moment. The dipole moment is the discrete version, right? polarization is kind of like the thing that's the version of it that's spread over space, akin to charge density. That's what polarization is. So the relationship, I wrote it here, the relationship between polarization and a discrete dipole moment is the same as the relationship between a discrete point charge and a charge distribution. Okay. So we have a dipole moment, discrete dipole moment. It's going to be hard to write because I find it always hard to write and writing differentiate between capital P and small p, but I'll try. So it's like represented by small p, and then you smear it over a volume. So let's take a small elemental volume, and capital P polarization is a dipole moment density. So this is capital P. So this is a dipole moment, similar to charge density. Here we have a dipole moment, and then we have a dipole moment density. It's essentially the sum in this small region of space, the sum of the n dipole moments that exist in this region of space divided by delta V. That's essentially what it is. Each dipole moment, each individual dipole moment goes to 0, right? But there's an infinite amount of them, and it goes to infinity. So in every small region of space, we have an infinite amount of dipole moments. Each one of those goes to 0, but there is an infinite amount of them. So they all combine into a limit. And this limit is called polarization. What units does it have? Well, so this is a density. So the dipole moment we said has Newton per meter, right? Remember, P equals magnitude P equals the charge times D, the distance, right? So it's sorry, Coulomb meter, not Newton meter, right? And this is a density, so it's over space, so it has to be divided over meter squared, meter cubed. So the dipole, the polarization vector has units of Coulomb per meter squared. Aha. Notice that the polarization vector has the same units as D. That's what D is. D is, that's what the flux density is. The flux density is actually a kind of polarization. It is actually the polarization of those bound charges in free space. Okay. So let's kind of recap a bit. We did, I mean, to do the P, we calculate P, we have to go back and remember the equation that we got for the dipole moment. So remember, we did that. We did that for, so if I have space, and then I have a dipole moment here, small p, and then I have a point in space, I need to find the ED in space. And then I need to know what the distances are capital. So ED, we did that, I think. Approximately equals 1 over 4 pi epsilon naught r cubed. That's one difference between a point charge source and a dipole moment. Dipole moment is proportional to the cube of the distance. And then the equation was 3 r dot p over r squared r minus the polarization, small p, let me ensure that it's small, volt over meter. Right, so this is for a discrete dipole moment. Okay, how do I deal with a distribution of dipoles, a polarization? How do I get the field of that? Oh, by the way, for the small region of space, what is the relationship between the dipole moment and the polarization? Well, the polarization is the dipole moment density. So you just integrate over the volume. So integrate capital P over the volume, you get small p for that volume. Okay, total P. Right, and P is a distributed source for E, akin to the charge density. Okay, so P is as important as a mathematical model of materials. So, and free space is considered a material. So in free space or a material, you might have dipoles. And then if you know P due to those dipoles, that's one way of characterizing the material. The question is, how do we incorporate the concept of P, of the bound charges, into the postulates of electrostatics? And the key concept here is the key concept here is, we cannot do that. But the key concept here, if you go back to the electrostatic postulates, rho v over epsilon, there's no way to incorporate polarization in there unless we can incorporate it through charge density. So if we have material or space, and we know the capital P vector everywhere, the only way to incorporate the effect of P into this equation is to somehow figure out, does P introduce any charge distribution? So you have a bunch of dipoles, and they stretch and orient in different ways. As they stretch and orient in different ways, space, do they result in a net charge density? If they result in a net charge density, you can use that to incorporate into the fundamental postulate, right? So the key is, can we find the relationship between P and the bound charge density, not the free charge density, bound charge density. Here, this is the total charge density. The total charge density in space can be divided into the bound charge density due to the polarization of the material or the medium, and the free charge density, the density that can move everywhere, right? So as we said in classical EM, the medium is not empty. Medium is not empty. So the medium, you can imagine it as a grid, 3D grid. At the center of each point in the grid, there's a dipole. And then when you have an electrical field, the dipole orients and stretch at every point in space. So the distance here, D, approaches 0, right? So, and the number of dipoles approaches infinity. This is the picture that we were talking about. And then we can redraw this and draw the dipoles as arrows. Actually, it will be easier to see, rather than drawing the dipoles as a blob. So at each point of space, we have differently oriented dipoles. When you take D going to 0 and N going to infinity, you get capital P, the dipole density, the polarization. So the idea, you have an external field and they orient in some way. When they orient in some way, you might have like two points. You might have a dipole that stretches one way, but then you have a field that's weaker in the other point, and it stretches differently. Because it stretches differently, if they both stretch equally, you have still an equal number of positive and negative charges. If this is stretched more than this, you might have a net charge at that point in space. That's essentially how the stretching of the dipoles varies. Might net you some charge in that point in space. So how do we calculate that? So the idea is that E, the electrical field, leads to P due to bound charges. So again, we said we're only concerned about polarization of bound charges in space. Okay, this is called the dielectric model. Okay, in empty space, E leads to some polarization of the bound charges of empty space, and this P is equivalent to D. So ultimately, D is a form of polarization, and we relate D to E by this epsilon constant. Okay, so epsilon is really a measure of how the electrical field polarizes space. That's the best way to put it succinctly. Epsilon is a measure of how the electrical field, how much the electrical field polarizes space. Okay, now the question is, as we said, we want to tie now polarization of materials to the fundamental postulate of electrostatics. It's going to be easier, and we said the way to do that is tied to polarization. Our entry, the doorway that we can use to enter into the postulate is if we can relate polarization to bound charge distribution. You know, if we figure out how the polarization distribution is, that might give us a net charge that's distributed in space, and that net charge can allow us to enter into the postulate and include P into the postulate. It's turns out that the easiest way of doing that, how much charge do I get? Do I have 34? The easiest way of doing that is to go back to the concept of voltage, right? So we introduced, so it's all polarization is a kind of dipole, right? Distributed dipole. Remember, we introduced the field due to a dipole electrical field, but then we introduced later the concept of a voltage. We want to redo, so we want to find the voltage of a dipole. It will be easier now to deal with the voltage of a dipole. So can we calculate the voltage of the dipole? So it's worth it to kind of do this calculation again, but for the voltage. So it's a nice exercise. Let's do it again. So I have the z-axis. I have my dipole. Positive part, negative part. I have the center origin. I have d over 2, d over 2. This is d. Okay. I have my point in space, P. And then I have the center from the distance from the center of the dipole. Let me actually make some space here because I'm gonna do a subtle argument here. So this is d over 2, d over 2. Okay, so this is the distance, the vector, position vector from the center of the dipole to the point in space. Then I have here dot, dot. So this is going to be, what is this? This vector, well, this is here d over 2 plus something should give me r, right? It's vector addition. So this d of 2 plus something should be r minus d over 2. So d over 2 plus r minus d over 2 gives me r. Same thing here. Here I'm going this way. I have a minus d over 2. So minus d over 2 plus something should give me r. So this needs to be r plus d over 2. A key concept here, geometrical concept, is that this whole thing is at an angle of theta, some angle theta. Because the distance is so far, those three lines are almost parallel. So this and this and this are almost parallel. That's the definition of parallel lines. Parallel lines are lines that intersect an infinite distance away, a very long distance away. So those three lines, because they intersect, this point is so far away from the dipole, those three lines intersect at a very far point. So those three lines are approximately parallel. At least close to the dipole, they're approximately parallel. Looking, if you shrink yourself and stand next to the dipole, the three lines emanating from the center and Q plus and Q minus look as if they're parallel, right? So the idea is that if you project Q plus into this here and project, right? So if you do this projection, really R capital is the same as R minus D2 with some extra distance here. Right? Right? Or R minus D over 2 is the same as R minus this distance, essentially. Okay. If you extend this down here, R plus D2 is the same as R plus this distance. So how do I do that actually? Okay, this theta equals this theta, sorry. This theta equals this theta because the lines are parallel. And then you extend something here, 90 degrees, right? So it's clear that this vector here, up here, is the same as R minus this segment. And this vector here down here is the same as R plus this segment, essentially. So this is how the upper vector and the lower vector differ. What is VP, total VP? We use superposition. So it's Q over 4 pi epsilon naught. I know I'm redoing this, but it's good to go review it. R minus D2. Well, I'm doing it for voltage, not for, what do you call it? The electrical field intensity. Volt. That's essentially what V is, the charge over the distance, 4 pi epsilon. And then we said we had the approximation that R minus D2 inverse is approximately, so the upper one is essentially the same as R minus this segment here, this segment. What is this segment? Segment is D, this is D cosine theta, right? Well, D over 2 cosine theta. So this is going to be, this has value R minus D over 2 cosine theta. What is this extra distance here? This extra distance, which is equal to that, is D over 2 cosine theta, but we add it, right? So this is going to be minus 1, and then R plus D over 2 minus 1. So this is approximately R plus D over 2 cosine theta. So the upper one is smaller than R by this small distance. The lower one is larger than R by this distance. And I can take R out, so this becomes R minus 1, R minus 1, 1 plus D, 1 minus D over 2R cosine theta inverse, and then 1 plus D over 2R cosine theta inverse. And then the second approximation that we said we wanted to do is the binomial approximation. We have 1x plus x to the power n, where x is small. This approximately equals 1 plus nx. This is called the binomial approximation. So in this case, n equals minus 1. The exponent is minus 1 here, minus 1. And then x is plus minus d over 2r cosine theta, right? So using this approximation, Vp becomes q over 4 pi epsilon naught. Instead of this, I have R inverse, which is R, and then this is going to be 1 minus n is minus 1 minus becomes plus d over 2 cosine theta minus 1 minus d over 2r, 2r cosine theta over r. And this we can sum it up easily. Before this approximation, it was like almost 0, but we get the difference between really two large numbers. So this becomes 1 cancels with 1, and then d over 2r minus plus d over 2r. So it's going to be d over r. So this becomes d over r squared cosine theta. What does this look like? So this looks like 1 over 4 pi epsilon naught squared, r squared. Notice, curious, the voltage has r squared. So remember, Coulomb's law, the field has r cubed in it, which is different than a point charge. Here the voltage has r squared in it instead of r, 1 over r. And then I have here qd, I take the qn cosine theta. This looks like a dot product, right? QD is the magnitude of the polarization, right? And this looks, there's a cosine. Whenever you see a cosine, that's like a dot product, right? So I can rewrite this as VP equals the polarization, it's a small p, not polarization, sorry, dipole moment. This is small p dot. So this is a dot product with what? So this is the magnitude of p, and there is the magnitude of r, right? So this is the magnitude of essentially dot qd with the direction here, r hat. Dot r hat over 4 pi epsilon naught r squared. This is the voltage due to a dipole moment. If I have a small volume, we don't have a dipole moment, we have a polarization. So the polarization, capital P times dV prime, is going to give me the dipole moment. Okay? So this is good, but we want to find the V due to polarization that rather than V due to a discrete dipole moment. So how do we go? Let's go ahead and start it. Even if we don't finish it, we can start it. 23%, and we have maybe 10 minutes. Okay, let me start this. Okay, so space. Space has some polarization. Now the idea is, at a point in space, P, we want to find what is, so we have the field, the voltage due to a dipole moment. But we said in space, we have polarization, dipole moments that are distributed. Well, we can, how do we get around that? Well, at a certain volume of space, small volume, we have polarization, right, in the space, right? But at a certain dV prime, that's, I don't know, a distance r away, and this is r hat, right? So this is dV prime. We do have a dipole moment here. The dipole moment is just, the small p is just the capital P times dV prime. That's how you get from a polarization to dipole moment. You take the dipole moment density, which is the capital P, the polarization vector, you multiply it by the volume, you get the dipole moment. And now we know what is the voltage at point P due to this small volume, right? So this is not the total voltage at point P, this is the voltage at point P due to the small volume at this location. So we say D, small d, Vp, the voltage at this point of space, dVp, due to this small volume of space, distance r away. We know how to do that. This is small p dot r hat over 4 pi epsilon naught r squared dV prime. Okay, this is the infinitesimal voltage. What is the total voltage? You integrate over all space. That's the trick. So if you integrate over all space, you move dV prime to every point in space and you integrate. The total Vp is going to be integration over all of space, capital P. This is capital P. This is capital P, polarization dot r hat, right? dV prime, capital P times dV prime is what gives you the moment over 4 pi epsilon naught r squared volt. This is equation number 1. What are we getting to? What we're getting to is that we want to tie polarization to charge density. The trick here is to remember, what if it was a space that is not, that has charge density? What was the equation for Vp? Vp was 1 over 4 pi epsilon naught. Vp is the integration over all of space of 1 over 4 pi epsilon naught of rho v dV prime over r. The key concept here is that to find the equivalent charge density due to polarization, you have to compare those two equations. The voltage should be the same, should be equal. The voltage should be the same, right? Come on. What's wrong? I think I need to charge my computer. I think it's sluggish because its battery is about to die. But this is the concept. The concept is that we calculated the voltage at a point in space due to the polarization of the space, and then we compare that voltage. We compared that formula to the formula of the voltage due to a distributed charge density, and that's how we find any charge density that arises from polarization. We just compare both cases should give me the same voltage. Whether I calculate the voltage from the charge density that arises from polarization, or I calculate the voltage from polarization directly, I need to get the same number. So I need to compare those two integrals and make them equal. So when I do that, I notice this tells me that the equivalent charge density due to polarization over space, right? Just compare those two integrals, right? So I have R here, I take R out, right? What's left? I have 4 pi epsilon, I can take it out. What's left is P dot R hat over R. Right? So using this trick, using the voltage, we determined if I have space or medium or whatever, and then I know what the polarization vector is at every point in space, I can find the equivalent charge density, bound charge density due to polarization. I can find that equivalent charge density from P dot R hat over R. Right? So at this point in space, I find rho PV by taking every other element in space, taking the distance R, taking P dot R hat divided by R. That gives me the charge density at that point in space, essentially. Let me see. Yeah. So the way we did the integration is that we have P, we have dV prime, we integrate over dV prime, right? So the charge density here, okay. So we have space, we have point P, we integrate over dV prime. So the charge density here at dV prime that we're integrating over turns out to be P at this point dot R hat over R. Okay. So this is not a very useful equation. I mean, what does this mean? I mean, how can we tie this? This is still not a total useful form. We're going to get to the useful form, but this is a step towards the useful form. All this is telling you is that you can tie charge density to polarization this way. You select a certain point in space, any arbitrary point, and then you go over the volume. At each point, at each infinitesimal volume, you take P at that inside that volume, capital P, inside the center of that volume, dotted with R hat, and then divided by R. P can be, the curious thing here is that P can be arbitrary, right? This is still not the final form we want to get to. And then there's another subtle point. If I have a volume, I might have a polarization inside the volume. And that polarization might lead to a charge density, polarization charge density. The way the things are polarized leads to a net charge density. But what happens on the boundary? What happens on the boundary is you might have something like this. You might have the orientation such as all the positive charges are touching the boundary. So might end up, you might also end up with the surface charge density due to polarization. So this is rho PS. So not only you might end up with an equivalent or a net volume charge density inside the volume, at the boundary of the volume, depending on how your polarization is, you might end up with a surface charge density. Volume charge density as Coulomb per meter cubed. This is Coulomb per meter squared. Okay, so we need to also to figure out what is the resultant equivalent surface charge density. This is the final calculation, derivation. And it's a bit of a subtle one, so I don't want to start it now. I'll start it next time. All right, so this is not the end. I mean, this is, we're gonna reach the end point for dielectrics next time, but we're halfway there, I would say. All right, let me see. Thank you, guys. I'll see you Wednesday. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, have a good day. Bye.